So good morning. Welcome to Krishna's classroom. I am Krishna. We continue from where we left last time. I was talking about two fascinating examples. One of them I have done yesterday. And today we take up the second one. And the second one is a very, very fascinating one. And sometimes even people think, do you have such objects existing? And that's the beauty of mathematical analysis. You have such wonderful pathological cases that keep the subject very, very lively, and a lot of new questions emerge. Now this is essentially the construction of a function on a compact interval which is continuous everywhere but nowhere differentiable. Continuous function, continuous nowhere differentiable function. Now, you know that if you have the graph of a function, there's something like this, something like x, f of x. There's a point on that. Now you see that the tangent, the slope of the tangent corresponds to the derivative of the function at the point x. This we know. So geometrically, it has something to do with the tangent. Therefore, what happens to a tangent? Suppose a function is sharply turning around. Then what happens is that the tangent changes its direction completely as it moves through this point. Now you see that the tangent turns around completely, or the slope of the tangent will be from positive slope to negative slope. It just passes through 0 and then just changes sign very rapidly. Therefore, if you were to think of a function which has a very sharp peak, something like this, here, then you see that the slope of the tangent will go from nearly plus infinity to minus infinity, because it is tan theta. Okay? So how to make it non-differentiable? One way to make it non-differentiable is that the right derivative at that point is different from the left derivative. But another way of doing it is that the sharpness of this bending can be increased. Now we will see how it can be done, and that will lead to what is called the sort of the tangent turning around and changing its slope very rapidly from plus infinity to minus infinity in this case. Okay, the range is the peak we have drawn. if you have a peak like this, then it will be going from minus infinity to minus infinity to plus infinity rapidly. So these are the two types of. So one way to break down the differentiability of an otherwise continuous function is to make it oscillate very, very rapidly. Right? That is one way of doing it. Now let us see how we can achieve this. It's a fascinating question. Now let me take this out and then go on with the construction. So we define now if you look at draw the graph of this function, it is like this: -1 to +1. The graph of the function is having a sharp peak here, in no differentiability for this function at that point, but it's a continuous function. Now what one does is extend this periodically to the whole of R. Okay, so that's the next process. Extend by the entire real line R by requiring that you are asking for the function or extending the function over the whole interval using periodicity. Then what do you get? Then this is what you end up with. -1, -2, -3 and so on. 1, 2, 3 and so on. You have the function defined like this. And then you have it defined like this. Then you have it defined like this, and so on, and so on. So now you have a function which is continuous on the whole interval -infinity to +infinity, and fails to have derivative at all integer points. Because you see that because of the sharp peaks appearing at that point, you have non-differentiability. Okay. Now we also look at this function, and we have this. Then we have some estimate of this function. The estimate of this function is phi s minus phi t is always less than or equal to mod s minus. Now this is very easy to do because the function is mod x or its translates that you have, so you can quickly prove this. So give a proof of this. For example, you have mod x, mod s. The second triangular inequality, use this, and then periodicity. So phi is, so this in turn tells you that phi is a continuous function. Continuous function, as we have observed here, it's a continuous function. The way in which it has been extended, it's a continuous function. Not only that, this gives a proof of, okay, that you have this inequality, and to conclude that phi is continuous. Now you also observe that mod phi, or rather phi is a non-negative function. So also it's a bounded function. It's non-negative, bounded between 0 and 1. Okay. Now from this we construct a new function. So now define f of x using this phi. This is equal to sigma. It's an infinite series. Imagine 3 by 4 whole to the power n phi of it's an infinite series. Now for clarity, let me write down the terms of this, the first 2-3 terms, then it will be clear. That is f of x equal to, for n equal to 0, you get phi x plus, for n equal to 1, it is going to be 3 by 4 phi of 4x plus 3 by 4 square phi of 16x, that is 4 square x plus etc. Okay. So it is interesting to see a new function has been constructed from the phi that we have defined through as an infinite series. Now let us examine what these functions are. Okay, but before that, let me just make some statement about this. Now you see that if you can simply see that this is true, that is mod f of x is less than or equal to, what you have is sigma phi is bounded by 1. It's all positive terms, therefore you have 3 by 4 and this is finite, hence convert this uniformly. Therefore, Now you know that this is considered as the uniform convergence of a sequence of functions which are continuous, and the sequence of functions are obtained as the partial sum of these series, and they are all continuous, and uniform convergence assures you that phi is implies f is continuous. So that is the first part of it. So we have constructed a function which is uniformly, which is described in terms of a series which is uniformly convergent, and the series and that gives a sequence of continuous functions, and therefore it's a continuous function defined on the whole of R. It is bounded. This lies between probably I think at most it is 3 or something. It's a bounded function. Depends on the bound for this. Isn't it? Now what we want to prove, but before that, before we proceed further, let us see what happens to the successive terms of this. The effects we have seen. This is your phi x. Now what happens if you take phi of 4x? Phi of 4x, and in fact we can take it as 3 by 4. So let me mark here 1. This is 3 by 4. So let me import this line, and then let me mark up. What about phi of 4x? Phi of 4x is you get phi of 4x is equal to mod 4x. Okay. So we are now, where is this defined? This is primarily defined on the interval -1 to +1. Therefore, phi of 4x you will define over and then it is bounded function. So over this interval the bound is given by 1, therefore it is bounded by 3 by 4. And so you see that this function takes this form, and then of course extend it further. So we have 1 by 2 minus 1 by 2, then 3 by 4, then 4 here, and then 1, 1. So Let's see how this function looks like. Okay. So you have this see over the interval -1 to 1. Now the number of discontinuities has increased for the second term. Okay. For the third term, it will further increase. Now it's worthwhile to look at what this is also, and then have an idea of how this functions. So what happens is that as n increases, you have this function that is 3 by 4 to the power n, 5 4 to the power n, x will be something like this. Very sharp. Even within one interval of length 2, you will have so many oscillations. Okay, and the height of this will be 3 by 4 to the power n. And then you will have 1 by 4 to the power n and minus 1 by 4 to the power n. So this distance is this is minus 1 by 4 to the power n. And this will be minus 1 by. So it just starts oscillating more rapidly, and there is more and more rapid breakdown of the differentiability of the function. There are more points where the function fails to be differentiable. So it's such a function. So this is fabricated, f is fabricated as a sum of this, and we have already seen the convergence of this. We have already seen that it eventually gives you a continuous function, nevertheless, in spite of all this. But what we are expecting is that the non-differentiability to spread everywhere. Okay, so we expect f to have not differentiable this is our expectation. All that we need is to differentiate. So we've got a continuous function which we expect to be non-differentiable. So let us see how this part is done. So we choose an arbitrary x. So fix x belonging to and a positive integer. As I said, what is happening is, see that the derivative which corresponds to the slope of the tangent will start turning very violently, fluctuating between large negative numbers to large positive numbers. So that's the problem. And vice versa. Therefore, we will see the differentiability eventually breaking down. And that's what we are expecting. So we choose an x belonging to R and an m belonging to. No, it is an arbitrarily chosen. Now we prove that at this point the function is not differentiable. Since the choice of x is arbitrary, it would follow that the function is nowhere differentiable. But now it is just a construction and looking at the derivative. So we choose a number, put some notations, delta m as plus or minus 1 by 2 minus this. So we have already fixed the number. Now how do we choose the sign? So we have to fix the sign also. We do it as follows. We fix the sign as follows. The sign is chosen such that no integer lies between x 4 to the power mx and four to the power m x plus delta m. So see, x is chosen, therefore you have also fixed. So let this be some 4 to the power m x. Okay, now we want to choose positive sign or negative sign here for delta m, depending on the following factor. Now you see that 4 to the power m x is certainly lying between some m this is possible. Okay. So now what about 4 to the power m delta m? 4 to the power m delta m therefore you see this is placed somewhere here and maybe m here and m plus 1 like this. Now you see that if it is over here, now we will choose the sign to be plus, so that 4 to the power m and 4 to the power m x plus delta m plus 4 to the power m delta m. This is 4 to the power m into x plus delta m lies between m and m plus 1, so that there is no integer coming in between. Okay. If on the other hand, suppose 4 to the power m is here and suppose m is here, m plus 1 is here, then it is on the other half of it, then you choose delta m to be minus 4 to the power m delta m to be minus half, so that you see this is 4 to the power m x delta m. First delta m is chosen minus, so that once again between these two numbers there is no integer. So that's how we choose. So the sign is chosen such that no integer lies between. Therefore, once we have fixed your x, the sign is also fixed. Either it will be plus or it will be minus, depending on what x is and what is the positioning of 4 to the power m x. So that's something to keep on in mind because we will be using this. Now note that when we define another function, define the following function gamma m, define this as phi of 4 to the power n x plus delta m minus phi of divided by okay. So this is a new function that we define, and eventually what you are trying to do is to let m go to infinity so that delta m goes to 0, and you show that this ratio actually gets broken. That's the strategy that we are going to adopt. So let us see how we do this. Okay. Now we first observe the following. Yeah. Sorry, not this. I think I said wrongly. It's not gamma m, but what we are going to work with f. So we are going to work with the following. Eventually we want to analyze this. Therefore, and look at this as so that derivative comes. If the derivative exists, if the limit exists, then the function is differentiable at x. If it doesn't exist, then of course it is not differentiable. So this is our strategy. So this is what we are going to explore. So in that we will choose a function gamma n like this. It's an intermediate construction, and we will analyze this function. For n greater than m, what happens? Look at that function. Okay. For n greater than m, you see that 4 to the power n is an even integer. Because just go to the definition and multiply by 4 to the power n, and then use the fact that n is greater than m. This is, and phi is of period 2. Okay, so that's how we have extended it. Therefore, what happens? You see that phi of 4 to the power n x plus 4 to the power n delta m minus phi of 4 to the power n x. So they are equal. Therefore, gamma n. I think this is gamma n. Sorry, this is not gamma n. This is gamma n. So hence gamma n equal to 0 for n. So this is one of the sets. Okay. Now you see it has all to do with this infinite series in managing it. Okay. Now for 0 less than or equal to n less than or equal to m, we are trying to work out components. What you have is that phi s minus phi t is less than or equal to cos s. And this implies mod gamma n is less than or equal to 4. Why it is so? See, phi s minus phi t, so you calculate this mod gamma n. Gamma n will be the modulus of this. Okay, and you have n less than or equal to m. Therefore, you see that 4 to the power n delta m and minus, okay, this function you take, and then you see that look at this condition, this is less than half and so on. You use this condition and then you get eventually that, okay, let us estimate this and here. So you should have, that is mod gamma n is equal to phi of 4 to the power n and this of course is modulus of because we use this condition, the way in which you have chosen delta n divided by, and this of course is less than or equal to 4 to the power n. This is minus equal to. So this inequality is satisfied. This is done. Now we look at gamma m. This is equal to now this you can easily estimate, and this is equal to so these are some of the estimates that you have. In fact, we are trying to estimate the various terms of the series. Okay. Therefore, now let us estimate this. You write down the series here. So this is equal to, in fact, this is sigma 3 by 4 whole to the power n minus this. You can see these are the terms of the series that is coming, and divide by delta m. This is the one to be seen. Now here again, you see that when n is greater than m, you see that this term becomes, this ratio becomes 0. That is gamma n. Gamma n for n greater than n is 0. Therefore, this is equal to and that's equal to, you can actually work it out. If you want, I can write one more step. No, because the terms for n greater than n we use that. Okay, therefore, this is equal to sigma minus 1. We will split it up. Isolate this term. Therefore, now you see we have seen that gamma m is gamma n equal to 0, gamma m is 4 to the power n. So we use that. So we use that this is equal to sigma n equal to 0 to n minus 1 3 by 4 to the power n plus into gamma m. Gamma m is 4 to the power n. Sigma can be written as 3 to the power m minus this. So this is greater than or equal to 3 to the power m minus sigma equal to 0 to m minus 1 and this is greater than or equal to e to power m minus if you have gamma n to the power n. Yeah. So we use that. Okay. So we have compute this. So what do you get? To compute this, this is equal to and this is equal to half of e to the power m plus. So one gets this inequality. So what you end up with is the following: f of x plus delta m minus x. This is greater than or equal to half of e to the power m now as m tends to infinity, delta m goes to 0. Therefore, if you go for the derivative of this, therefore limit does not exist. Okay, that is f is not differentiable the choice of is arbitrary and hence f is nowhere differentiable. So that is what it is all about. The f that we have constructed fails to be differentiable at any point, in spite of the fact that it's a continuous function. And this is one factor that you look at in both these examples, the example 1 and the example 2 that we have considered, is we make use of an infinite series. We also make the function to oscillate more rapidly, because the later on, as n increases, the nth term as n increases will start oscillating more and more rapidly, so that through this process in the example 1 you got discontinuity spreading everywhere. In the second example, we have seen the differentiability breaking down everywhere. So these are the two things. I mean, these are. So in both the cases, the mode of arriving at such a function is by inducing perfect oscillation. I wish to make some remarks on what we did. We considered two very fascinating examples of constructing certain functions with certain interesting properties. The second one we take up for comments. Let us see what we did. This is just a process which the students should do, that if they have proved a certain results, then they should revisit the proof and then make some analysis of that, so that sometimes it may be possible to bring some qualitative improvement on the proof itself. Anyway, in the process of learning mathematics, I think this is important that you understand at each stage what exactly you are doing. So, for this purpose, when by learning the proof of a theorem, I think you should revisit it, dissect the whole thing into bits and pieces, and try to understand why any particular thing has been done in that proof. Okay, so this is just a model for that. So what we are looking at is the example of a function, real valued function that is continuous everywhere, but nowhere differentiable. Let us recall the construction. The first few parts will go very, very quickly. We started with the function mod x, phi x equal to mod x on the interval -1 to +1. Then what we did was we extended this to the whole R using periodicity with period chosen as 2. So with the requirement that phi x equal to phi x plus 2, the function was extended to the whole of R. So having got that function on the whole of R, the next step is to define a new function f of x in the form of an infinite series, which is defined here. It's 3 by 4 to the power n phi of 4 to the power n x. Now one quickly observes that this is a uniformly convergent series. I mean, that's a simple thing to do because of the 3 power 4, 3 by 4 to the power n factor coming with all these functions, and these functions are bounded functions, bounded by 1. And therefore, it is quite easy to see that it is uniformly convergent. The consequence of this is that you see that every partial sum of the series is a continuous function. So you have a sequence of continuous functions which uniformly converges to something, and therefore the limiting function is uniformly continuous. And this is one of the very strong theorems that we do in analysis. Okay, so it's a consequence of a major theorem. Now if you look at what has happened here, what are these terms? See, as n increases, phi 4 to the power n x will start getting more and more points of non-differentiability. So the peaks will start appearing. So it will be something like this. Yeah. So if you just take the f1 is 3 by 4 phi 4x, then you see that the basic function will be defined on the interval -1 by 4 to 1 by 4, and with the period 2 it is extended all over the function, all over the real line. So that's the nature of the function. And if you take the third term, then what happens is it is the basic function is defined on the interval minus 1 by 16 to 1 by 16, and then extended over the whole interval with a period equal to the period equal to 1 by 8, and so on. So it's very clear. So what happens is at each stage when you extend this, what you get will be a function which is more or less like this. Functions of this kind coming, which means more frequently points of non-differentiability will occur. It is non-differentiable here, non-differentiable here, non-differentiable here, and so on, and multiplied by a factor 3 by 4 to the power. So this is how the function looks like. Each of these terms look like. And now it is the sum of these functions which eventually we are not able to draw this function, but what we understand is as n gets larger and larger, the points of differentiability will be spreading all over from minus infinity to plus infinity. That's the important observation that we make. Now that's about the continuity. So the continuity of the function is now assured. Now we are going to play around with this function. Our claim is that this f that you have defined here is not differentiable at any point on the interval. So obviously the thing that you have to do is look at this limit, f of x plus epsilon minus f of x divided by epsilon, limit epsilon tends to 0 for any arbitrary point x. If you can prove that this limit does not exist, then you are done, and that's exactly the strategy. But now you see the hard part of the analysis comes. What one does is very cleverly choose this epsilon, or this is actually epsilon going to 0, which is replaced by a sequence delta m going to 0 as m tends to infinity. So we choose this delta m. How do you choose this delta m? What is the logic behind choosing this delta m? So for that, what one does is look at this. And this consists of this series. So these are the typical terms of this series. And this is really replaced by, this term is replaced by gamma n that we define in the proof of the theorem. Now you see that we have chosen, because we have the periodicity of these functions readily available. So our task is to choose delta m, the sequence delta m appropriately. What you do is choose delta m in such a way that this infinite series will reduce to a finite sum. And that's what you have proved, that this gamma m, which is this, okay, gamma n is equal to 0. So this is called a gamma n. Gamma n equal to 0 for n greater than or equal to greater than. That is, using periodicity, you see that the later terms of this. So what is the consequence? The consequence is that this infinite series will become a finite sum. And now it is easy to estimate it. And this is the estimate that you obtain, and you show that this is in fact greater than or equal to, yeah, this is what you have. This is greater than or equal to half 3 to the power m plus 1. This is because of the inequalities that you have, namely mod gamma n is less than or equal to 4 to the power n. In fact, mod gamma m equal to 4 to the power m. Okay, so we make use of that. We make use of that and then get the estimate of this. So we get an estimate of this, worked out to be this. I mean, this is the hard part of the analysis, which is inevitable while doing analysis. Because there is some part of our proofs which will be supported by grand theorems. And that's what is called the soft analysis. The soft analysis will take you sufficiently deep into the proof. And at the end, you often come across the requirement to do something really, what you call something very unusual or things like that. So you may have to, for instance, the construction of the idea that of reducing this infinite series into a finite sum is one such idea for which you have to choose the time appropriately. But at the same time, you know, the desired objective of limit epsilon tend to 0 f of x plus epsilon minus f of x divided by epsilon is estimated. And then we prove that this is the inequality. So often it is playing around with inequalities that is at the heart of doing mathematical analysis. And what happens when the time tends to 0 corresponding to m going to infinity? You see that this term will become bigger and bigger as the time goes to 0, because it is, you know, its absolute value is bounded below by half of 3 to the power n minus 1. As m tends to infinity, this will get grown up. So this will always stay on the other side. Okay. Therefore, eventually this does not tend to a limit. That's how you prove it. But what I wanted to impress upon you is this. Every proof has to be analyzed in detail. This is one way of learning mathematics. Having worked out the proof, break it down to various steps and then analyze each one of the steps and go for the reason for that. This is one thing, something in mathematics. In mathematics, nothing is done without a valid reason. There is no magic pill at any stage at all. I mean, I am talking to the students, not to the expert mathematicians. Okay, so this is how the proof has been done. And you can see some similarity between the two examples that we considered. In both the cases, we make the function to oscillate more rapidly. We work with an infinite series. And this is clearly one of the techniques to, you know, building up new functions with a desired property. Here, your objective is to get the function non-differentiable at every point. In the previous examples, our objective was to get the function discontinuous at a countably many points. Okay. In both the cases, this has been achieved by the construction of this kind. Okay, thank you very much.